Welcome to episode 2 of Charming Python. In this episode, we're going to be adding some tests, some automated tests using PyTest, which is a very commonly used Python testing framework. And as is always the case when you're adding tests to existing legacy code, we're going to have to make some changes to the code in order to be able to make it testable, because code that is written without tests tends to not be testable. If it is, it's usually by pure chance. And so we're going to have this little bit of a chicken and egg problem that many people run into when they're trying to add tests to code, which is, okay, I'm trying to add tests to the code. It's hard to add tests to the code. What do I do? Well, I have to change it. Well, how do I change it and not break it? Well, ideally, you would have tests for that, but you don't have tests. So the chicken and egg problem presents itself. So we're going to walk through that today and talk about how to add tests, and how to get our code into a state where it is designed to be tested so that we can make further changes to it with the benefit of having those tests. To get started, let's talk about how we're going to run our tests and what we're going to use to do that. So in the previous episode, which if you haven't seen already, you should go back and watch, we added a makefile to our project, and that makefile creates an environment for us, and it lets us manage our dependencies, and it lets us execute our code in an intersubjective way, a way that other people can reproduce easily. So what we're going to have to do here is we're going to have to add some testing tools to our makefile, and we're going to have to add some dependencies in order to run tests. I have PyCharm here open. I used PyCharm in the previous episode. We're going to be using that throughout the series. And I have my makefile open here. And the first thing that I want to do is add a target to this makefile that's going to let me run tests. So I'm just going to add that now. We're going to say that depends on the deps target, which will install our dependencies for us. And the way that we're going to run our PyTests is by running our tests is by using PyTest. We're going to run PyTest out of our virtual environment. So I'm going to reference that here and say in the vems directory, in the bin directory inside the vem directory, there should be a PyTest binary, and I'm going to run that with the -v flag just for a little bit of extra verbosity. And I'm going to put a little comment on here. As you may have seen in our first episode, we can have some of our targets that will actually show up in a little helpful menu. And to make that appear here, I'm going to say, put this comment here that says run tests. So now if I come down here and I do this, it should complain about PyTest potentially not existing. Well, I'll tell you what, let's do this just to make sure that we're doing this from a clean state. I'm going to blow away the virtual environment, and I'm going to run make test, and this should install that virtual environment, but it should complain, I think, unless we've added it to the environment file already, which haven't. It should complain that PyTest doesn't exist. So we're going to need to add PyTest as a dependency to our project in order to get this to work. But before I do that, I want to sort of make sure that there isn't something else going on, that this environment that we're working with doesn't already have it maybe, or has a different version of it than we might expect to install. So I sort of want to like watch this process not work before I make changes to make it work. And that's going to be a common pattern that you're going to see as we go and as we add existing tests to existing code or write new tests, that before we add a test, we want to verify that the test is actually testing what we think it is, that the behavior of the system is the way that we think it is at the start before we go making changes to it, because it's sort of like the control step in an experiment. You know, if you're going to run an experiment, you need to have a control that says, like, you know, is this experimental thing that we're changing, does it actually have any effect at all? Because it might not. So this is the failure that we expect to see. PyTest command not found. That's exactly what we were looking for. So now what I'm going to do is I'm going to come over and I'm just going to add PyTest to my list of dependencies. And I'm going to save that. And I'm going to run this again. And hopefully what I should see now is that, A, it installs PyTest for me. So the makefile is detecting a change to our environment file, and it's doing the work to update that environment. And then once that work is done, as we run PyTest, we see that, in fact, PyTest does run. It just says, okay, you don't have any tests. That's great. That's exactly what we want to see. So I'm going to go and I'm going to add a test. I'm going to add a very basic test here in this test directory. And I'm going to make a test called test stimp meter. .py. And yeah, you can add that to Git for me. That's fine. And the syntax of PyTest, the convention of PyTest is that you write functions in your Python file, in your test Python file, that start with the word test, and then you can have anything after that that you like. So I'm going to just say test calculation. Doesn't even matter at this point. All I'm going to do is say assert false, because I just want to have something that I can run and see that the test will actually fail. So yeah, so we can see this confirms that PyTest is running our test. It sees our sort of assert false. It treats that as an error, and that's sort of the most basic thing that we would want. The next thing that we're going to do is sort of make this a little bit more real. But before we do that, what I want to do is I want to add another tool. I want to add another dependency to this. And that is a tool called PyTest Watch. What PyTest Watch is going to do is it's going to help us sort of speed up our development by running the tests whenever we change the code. And doing this, following this practice will have a number of different benefits for you. The first thing it'll do is it'll just save you time. You don't have to go and switch over to your terminal or click on a button, grab the mouse in order to run the tests. It's just whenever you make a change, it's going to run the test for you. Another thing that's going to do is it's going to help keep your tests fast. And how is it going to do that? Well, first of all, we should probably back up at least one level and talk about what we want from our tests. Like, what are we looking to gain? What properties do we want to have in the suite of tests that we create? And the way I like to think about this is we want really four things. So I'm going to go into the make file or the README file for this project, and just put a little developer notes in here, something to let the developers on this project, people who are changing this project, know, like, okay, what are the conventions that we're using? What are the things that we want to do? What are the things we want to avoid? Just to sort of have that be a place to share that information. Again, trying to be intersubjective, like try to put it in a place where everybody can access it. They all experience it in the same way. So I'm going to put a couple of notes in here about what we want our test to be. So we're going to say we want our test suite to be, and we're going to say we want it to be fast. And what does fast mean in this context? Well, fast means that we want to run hundreds of tests per second. That's what I mean when I say I want my test to be fast. Because in some contexts, a fast test is one that runs in 1 second, right? Like, there are lots of environments in which most of the tests take minutes or hours to run. And so, a test that's fast in that context would be a test that runs in 2 or 3 seconds. To me, that is a slow test. I want my tests to be so fast that I can run hundreds of them per second. That's a fast test to me. Another thing that I want is I want my tests to be informative. And what does that mean? Well, that means that each test demonstrates one single behavior in the system. It informs me whether or not that behavior is working or not working. And when it isn't working, it tells me like very clearly what's wrong, and it points out to me like, it explains very clearly like what is not correct about the behavior. So an example of a test that wouldn't be informative is one that maybe tests a whole bunch of different things, and if any of those things are wrong, it just says something's wrong, right? And there's lots of tests that are like this, and they're not necessarily bad, but that's not the kind of test that I want to write. I want to write tests that are informative, that say, okay, when this one specific thing is wrong, it says, I expected that when you add 1 and 2, you get 3, and I added 1 and 2, and I got 4, right? That's an example of an informative test, as opposed to something is wrong with addition. Well, that's not informative to me. So I want to say that, each test demonstrates one behavior in the system. Another property that I want is I want my tests to be reliable, which means simply, if things are working, I want the test to pass, and if things are not working, I want the test to fail. And I don't want anything else in the world to affect that. I don't want the state of some remote server on the other side of the planet to affect that. I don't want randomness to affect that. I don't want anything else to affect that. I just want the tests to pass when things are working and fail when they're not. And we'll talk about some ways to make sure that our tests are reliable later in this episode. So tests pass when they are working, or when the system is working, fail when the system is not working. And then the last property here is that I want my tests to be exhaustive. If I could spell exhaustive, that would help. I want my tests to be exhaustive. So I want everything that I care about in the system to be tested, and the things that I don't care about not to be tested. So one way that you can think about this is that you don't want to overfit or overspecify your tests. You want to test the things that are the important behaviors of the system, and things that are not the important behaviors of the system you specifically do not want to test. And the reason that you don't want to do that is because one of the great benefits of adding tests is allowing refactoring. What is refactoring? Refactoring is very specifically changing the structure of the code without changing its behavior. That's one of the great benefits of writing tests, is it allows you to verify as you change the structure of the code without changing its behavior that you have in fact not changed the behavior. And over specifying your tests makes this harder, because what happens is that you wind up making changes to the code that don't change the behavior. They just change the structure, or they change the format, or they change other things that don't affect the behavior, but the tests fail. And they shouldn't fail. They should pass. They should continue to pass as we make those changes. That's something that's going to give us the confidence to make changes, knowing that our tests continue to pass. So like, clearly I haven't changed the behavior because the tests are still passing. Well, if the tests fail when you do something that changes the structure, or changes the layout, or changes the formatting, or changes other things like that, then they're not as useful. So exhaustive tests test everything we care about and nothing we don't. So those 4 properties, fast, informative, reliable, exhaustive, summarized in the handy acronym FIRE, are the properties that I want my test suite to have. And so popping the conversation stack back a little bit to PyTest Watch, what is PyTest Watch doing for us? Well, one of the things it's doing for us, aside from just generally making things faster because we have fewer buttons to click, is making sure that our tests stay fast. One of the things that will certainly happen as you add tests is the more and more tests you add, the longer it will take to run your tests. Now, if you have tests that are good and are fast and run hundreds of tests per second, and you add a test that takes 1 second, if you're just running your tests every once in a while, you might not notice that, right? You might have this, and it is in fact very common to have this sort of power law distribution where you have a whole bunch of really fast tests, and then you have like 1 or 2 tests that are significantly slower than the other tests. But if the fast tests are really fast and that they're running hundreds of tests per second, if you're just running your tests every once in a while and your test time doubles or triples from 300 milliseconds to 1 second, or from half a second to 1 or 2 seconds, you might not notice it. But if you're running your tests on every change, you will notice it. It's almost like if you're typing an email and you have like your spell checker running, and all of a sudden like the editor just like freezes up whenever the spell checker runs, right? Like you would notice that, right? It would interfere with you. It would slow you down, and you would be like, well, what's going on here? And so the problem is that if you don't catch those slow tests at the point when you initially create them, it's very difficult and expensive to go back and sort of retroactively make them fast. So you need a feedback loop for the speed of your tests. And running your tests all the time is a great way to create that feedback loop. So we're going to use PyTest Watch as we work, and we'll be able to see, sort of down here, like how long are our tests taking. So you get this feel of how long it takes to make a change to the code, and we'll almost have like an emotional response when they get slow, and that's exactly what we want. We want our process to feel sluggish and slow and chunky when we add a test that takes a second or 2. So I'm going to go and I'm going to add another target. We've got this make test target, and this test target is going to be very useful for us. We're going to. Oh, did I change the environment file? Yeah, I sure did. So we're going to let that install make watch for us, but we're still going to need this test target, right? Like we're not going to run make watch in our continuous integration environment. We're going to want to have a way to sort of run tests in batch mode, and that's what make test is all about. That runs nice and fast. But I'm also going to want to add another target here, and I'm going to call this one watch, and I'm going to have that depend on deps as well. And I'm going to say run tests continuously, if I could spell continuously. Did I spell it right? I think I did. I can never spell that word. Anyway, so we're going to do that, and we're going to run PyTest watch out of our venv directory like this. Bin PyTest watch runner. And we're going to tell it to use PyTest because it can use other things, but we're going to tell it to run with PyTest. And we're going to tell it to ignore the venv directory. So one of the things, man, nothing like a screencast to just make you completely forget how typing and spelling works. So I'm going to tell it to ignore the venv directory because what PyTest watch will do is it'll watch your file system for you. And so I don't want it scanning that venv directory because it's just going to give it a lot more files to scan. There's actually a chance that depending on your operating system settings, you might exceed the number of files that that PyTest watch can watch at one time, and you'll get sort of a iNotify error. So to avoid that and to avoid it taking extra time to scan files that we expect will never change, I'm going to tell it to avoid that directory. So if I do this and now I run make watch. So yeah, you can see it ran the test, and it's sort of, there's no prompt here. It's continuing to run the test. So if I go back over here and I change this to true and then I hit save, you can see it immediately runs that test. The test passes. We can see how long it all took, and that's really good. That's the environment that we want. So as we change this, we can very quickly switch back this state back and forth. It'll just run all of our tests for us whenever we make that change. That's great. So this actually is a pretty good spot to commit. As I mentioned in the first episode, we want to make sure that we're committing often. We want to take very small steps, especially in the situation that we're in where we don't have our automation and testing in place yet. So if we make a mistake, we want to be able to easily roll back. But we're just going to commit this here and say adding tests and adding test and watch target to make file. Probably a good description. Cool. All right, that looks good. So make watch. Okay, so we've got our watch target. We've got PyTest watch installed. We've got our test target. We've got a test that has assert true and assert false in it. It's doing a few different things. What's next? Well, the next thing we're going to want to do is we're going to want to start looking at the code that we have and figuring out how we're going to write tests for it. So let's crack that open. We might have to make one more change to the make file in order to get this to work, but I'm going to wait. As I said before, I want to see that failure happen before I sort of speculatively go and make changes to the code. But I think we might have like a Python path thing that we need to change. All right, so I created this this golf subpackage in a directory here. It's not a package yet, but if I go and I make a new sort of dunder init file there, then Python will recognize this as a package. And the other thing that I need to do here, just to make PyCharm happy, is I need to change my interpreter. So you can see right now that we're using the system interpreter, the system Python, and we don't want to use that. We're not using that in our make file. We're not going to use that for our test. We're not going to use that for anything. And we want to tell PyCharm that we're not using it either. So I've already set up an interpreter here, but just to show you how to do this, you can click on this Add Interpreter. You can choose an existing environment. you can go and select the interpreter that you want to use, and we want to use the Python 3 that is in our virtual environment. I've already done this once already, so I'm just going to switch to that, but it's important that you do that if you want PyCharm to stay in sync with the rest of the project, our sort of intersubjective automation of the project. So yeah. All right, so now what we're going to do is we're going to change this a little bit. Now, this is, in theory, refactoring. In theory, what we're doing right now is changing the structure of this code without changing its behavior. However, in practice, this is not refactoring. It's not refactoring for two reasons. One is we're not really going to be able to avoid changing the behavior because we're going to have to change the way that this code is executed. Right now, if I go and I want to run this, I say, venv bin python 3 stimp meter like this, and I give it, a slope in percent grade, and I give it a speed in stimp, and I run that, and I get this result, right? And that's cool, but what we're going to actually, the first change that we're going to have to make to this is we're going to want to put it in a sub-package. We don't want to just leave it in the top level of our project. So I am going to want to run this like this. I'm going to say golf/that. And that's going to be different. Like, that doesn't work. So before I make any changes at all, I'm going to make I'm going to run this, and I'm going to capture the output of it. And what I'm doing here is a technique called creating a golden image. I don't want to do this long term for reasons that we'll talk about, but in this sort of period, in this sort of beginning period where we don't really have automated tests, we don't have our testing infrastructure in place, the code is not designed to be tested, I need something to sort of bootstrap the process, to break the chicken and egg problem. And so what I'm going to do is I'm going to create this sort of golden image by sending this text to, or sending the output to a text file. And then let's just look at that to make sure that it looks reasonable. So yeah, so this is when I run this program with these particular parameters, I get this output, and this is in a text file. And so what I can do to make sure that as I do this, I haven't broken anything. If I do a make run here, we sort of get the same thing, right? I think that's, did I use the same settings in my make run? 2 and 10? Yes, 2 and 10. So if I do a make run here, I get the same thing. And what I can do is I can just say, okay, well, we're going to do a diff of our golden image text file and the output of running make run. And I see no differences. Now, if I were to go in here and sort of break this in a very sort of subtle way, oh, this is the wrong file. This is a different file. This is the one we want to change. So if I were to go down and break this in a very subtle way, like maybe just change the casing on one of the things here, you can see that it shows that difference. It says, okay, you made a change, and now this output is different. And so what we're going to need to do here is we're going to need to do the minimum amount of refactoring, that is changing the structure of this code without changing its behavior, to get it into a state where we can test it. And this might mean doing some things that are a little bit weird, but the most important thing here is to not change the behavior at all. Because we have this golden image, and the golden image gives us this really wonderful way to say hey, everything's cool, everything still works. But that might mean that we need to sort of conform to this exact output, which is fine. We're just trying to get to a point where we can start writing more automated tests, and then we can be a little bit more flexible in the changes that we make. So the first change I'm going to make here is to just move this into this golf directory, and that will immediately break some things. So if I run this now, it's going to say, yeah, I expected to get all this output, but what I got was that file doesn't exist. So I need to go and I need to change my make file. I need to say, okay, in the make file, we have this sort of run example. I'm going to change the path there. And now we're going to run this again, and we can see, okay, cool, our golden image is still working. All right. So now let's go take a look at this file. So there's a lot of things going on in this file. I'm going to get my make watch running. There's a lot of things going on in this file. We've got this constant up here that's COF, stands for coefficients of friction. That wouldn't be obvious. We've got PyCharm here complaining about some things, saying like, hey, you're not following PEP8. Okay, that's easy enough to change. That should hopefully not be a big deal. We're saying, oh, we're shadowing variables from the outer scope. So we've got this variable here called stimp. We've got another variable here in the global scope called stimp. That's not great. We've got this variable v that is also shadowing. This says this phrase is duplicated. Unfortunately, this is this is how gravity works. So that is actually what it should be. This is saying we've got too many leading comments. Okay, just to make PyCharm happy here, I'm going to make that change. I really want to have as few of these sort of like little squiggly lines as I possibly can, because then they'll stand out. If I just have like a whole bunch of them scattered all over the code, they sort of blur together and you start to ignore them. What you really want is to shrink that down and really have these things be valuable and actionable. So like those variable names shadowing the outer scope, like, yeah, that's something that I want to change. And I want PyCharm to complain about that. And I don't want to sort of just ignore that and have like all these different things sort of on the screen. You can sort of see on the right-hand side, PyCharm will highlight all these things for you. So I want to make PyCharm happy, and I want to try to conform to that as much as I possibly can. So I'm just going to go and I'm going to sort of clean these things up to try to remove as many of these as I can right now, just to have PyCharm sort of help us out a little bit. Because again, we're in this state where we don't have tests. We don't have too much automation around verifying that this is correct. So I want to try to take advantage of everything that I can. And so right now I've made these changes, but my tests aren't really testing anything. I just have this sort of test calculation. The only thing that I have is that diff. So I'm going to run that diff again and make sure that I haven't broken anything by making those changes, and I haven't. That's good. So we've made a few changes to make PyCharm a little bit more happy. We've maybe cleaned a few things up. Now we need to start thinking about our approach to refactoring this code. And again, we're trying to change the structure of the code to make it more testable without changing its behavior. So there's probably a few things I can do to start organizing this a little bit and make it a little bit more, a little bit easier to deal with. So the first thing is I've got these print statements that are all interleaved inside of the calculations. And the first thing that sort of jumps out at me is like maybe there's a way to group the calculation together and the printing together so that I can test them independently. So I'm just going to reorganize these lines. I'm just going to move them and sort of group them and say, okay, I want to try to get all of these calculations together, and I want to try to get all these print statements together. I've also got this assertion in here that sort of is like making sure that we don't accidentally do something where the ball is never going to stop. The way that this simulation works is it basically loops while the velocity is greater than 0. And so if the velocity never reaches 0, then the program will never stop. And this assertion here is there to sort of guard against it, to make sure that the ball will never stop going down. I don't know if this is actually sufficient to keep this from happening. I kind of suspect that it's not, but I want to make sure that I at least preserve this as it was written. And that is probably a good test for us in the future, is to say like, okay, well, what happens when we pass parameters into this program that would cause it to simulate a ball that never stops rolling? So that's something I want to leave there as sort of a reminder for that. But let's run our diff again, make sure that this reorganization didn't break anything. It didn't. That's good. We're just making very simple changes at this point. Okay, so we have our calculation group together, and we have our printing group together, and we have this assertion there as well. Yeah, I'm even more convinced right now that this assertion really isn't protecting us from anything. I almost wonder if the way we should do this is yeah, I don't even know. Like by the time you calculated that the down distance is none, would it have even done that? I don't know. But I'm going to leave it there. We really just need a test to tell us whether or not we're handling this case properly. So we have our printing, we have our calculation, we have some sort of command line argument parsing that we're doing here by hand. And now we want to try to get some of this stuff tested. And so the first thing I'm going to do is I'm just going to write a test for this calculate function. This calculate function is a sort of a public function within the module. And I want to write a test for that. I might change this later. Oh, we got another PyCharm thing here. I might change this later where I change my mind about how we're testing this. But again, I'm trying to sort of break this chicken and egg problem. So I'm going to do this incrementally. So I'm going to go and I'm going to import, from golf import stimpmeter. And I'm going to say stimpmeter.calculate. And I'm going to give it the same parameters that we were using in our example earlier, just to keep things consistent. We're going to want to add more things later, but for now I want to just sort of keep it simple. And if I remember correctly, this thing returns a distance and a speed, as a tuple. Let's go take a look at that real fast. Yeah, distance and speed in seconds. So I'm going to make some assertions about this. And just to start, I'm going to assert that the distance is 1 and the speed is 0. And that will almost certainly fail. It better fail. I expect it to fail. And I just want to see that fail in my make watch. Oh, yeah. What's happening here is MakeWatch is very particular about import errors when you first start it up. And it has this really terrible property where it will just print nothing if you have an import error. Now, once you have it running, and if it sees import errors, it's fine with it. But when it first starts, it complains about it doesn't complain about this at all. So this is something you can run into, and I certainly have before. So we're going to run make test here because make test doesn't care about that, and it says no module make golf. This is the thing I was talking about earlier with the Python path. Now, there are many different ways to solve this problem, but you have to give Python some hint about where it should be looking for files when you say import. The way that I'm going to choose to do it here is by exporting a Python path variable in my makefile. So this is an environment variable, and I'm just going to export it so that it's available to Python. And I'm going to say that the Python path is equal to curter, and this is a makefile variable that we talked about in the previous episode that just represents the current directory. So now when I run make test, I get a failure, which is good. And I can run make watch now, and it should, I think, work. Yeah, and it does. There are lots of different ways to solve this problem. You can do, I think it's like sys.path. You can manipulate that. You can change your virtual environment with Conda in order to handle this. I don't know that there's a particularly right way. I'm sure there's lots of debate on the different ways to do it. I'm doing it this way. Your mileage may vary. At me if you disagree, kind of thing. But we need to do this one way or another. Otherwise, Python's not going to know where to look for golf when we say, from our test, when we say from golf import stimpmeter, it needs a way to know that that means this directory and this module. Okay, but we're importing the calculate method now, which is good, and we're passing our arguments into it, which is good, and we're getting some results. Now these results we can verify in a number of ways. The way that I'm going to do it is I'm going to look at our golden image. So we already sort of are taking as an assumption that this program was correct when we first got it. Maybe we verified it by hand. Maybe we went through a peer review process and people looked at it. But we're sort of taking it as granted that however this program was when we first got it is correct. So let's take a look at, now that might be true, and we can test that assumption later, but for now we're operating under that assumption. So what I'm going to do here is I'm going to look at my golden image, and I'm going to look at the distance and the speed, or the distance and the, oh, it's not speed, it's seconds, isn't it? Seconds, that's right. For those of you watching the screencast have been like, that's been wrong this whole time, Ben, and you just now noticed it. So yeah, so I'm gonna take a look at the distance and the time that this went, and we're gonna use that in our assertion. We're gonna assert that the distance is this amount, and that the seconds is this amount. And we're going to do a make watch. And I actually kind of expect this to fail. And it does. Why does it fail? Well, because floating point. Getting this is a really deep rabbit hole, and I could go into a lot of different things here. But like the most basic example of this, and I think this will just work if I do this here, is if I just say, if I assert that this is true, and in a regular decimal representation, you would expect that it would be true. It's not. And because computers, and you can Google this if you want. I will leave this as an exercise to the reader as to why this is true. But one of the fundamental things you need to understand about working on computers is that they don't represent floating point the way that humans would normally think that they would. And so we have to account for this. And the particular method that is used to do this calculation is not really a decision that's being made by Python. It's a decision that's being made by the operating system or the hardware in a lot of cases. The hardware architecture that you're on will determine this. And so getting back to our original sort of founding sort of properties of our test, we want our tests to be fast. We want them to be informative. We want them to be reliable. We want the test to only pass when the system is working and only fail when it's not working. This is a place where unreliable tests might creep into the system. Because what I could do here is I could say, all right, well, I'm going to take this out. I'm going to do this. And I'm just going to copy this floating point variable here. And I'm going to paste it into here. And I'm going to do that. And that one worked. And okay, fine. And I'm going to do the same thing for this. I'm going to do this here. And this is all fine, cool. And now the tests are passing. Great. But the problem is that if you run this on a different if you run this on a different architecture, you run this on a different piece of hardware, maybe a different operating system, sort of depends, you might get different results. And so whenever we're comparing floating point values, that's an opportunity for unreliable tests to creep into our system. We need to think about that. We need to prevent it. So what I'm going to do is I'm going to assert that it's equal to this amount of precision and no more. And the way that I'm going to do that is I'm going to use a built-in PyTest function called approx. So if I import PyTest in my test, and I say PyTest approx of distance, actually I think I might have this flipped the other way around. I think I want to say distance is equal to PyTest approx of this. And if I do that, then PyTest will compare this, and I think the default is actually 6 decimal places, so this is exactly what we want. If we wanted to be explicit about that, I think we can say I is -6, and that will give us the same result, and it does. But PyTest approx will compare floating point values to a certain level of precision, and for our program, this is actually the level of precision that we want, so that works out great. So I'm going to do the same thing here for the number of seconds, like this, and that's good. So now that we have a way to test our calculate function, the next thing we need to figure out is what more should we test. I think that condition that we were talking about earlier, where the velocity never drops below 0, would be a good one. I'm kind of wondering what it's going to happen when I do this. My I don't know, I'm like 40 delta that's just going to go into an infinite loop, but we'll find out. So we'll say test high velocity, and maybe there's a better name for that test. Naming tests is important if you want to make them informative. But for now, let's just do this. Let's just take this guy and do a calculate. And we're going to say that the slope is like 10% grade, and the speed is 13. So this is like the worst green at Augusta National, and that should just not stop. Well, it didn't go into an infinite loop. Let's see what the values are. They might be none. Just assert that they're equal to 1. That is unexpected. Oh, right, because this is uphill. That will definitely stop going uphill. The problem is downhill. Yes. Okay, so we are actually getting values of none here. So it looks like this function is currently resilient to this problem of if the velocity is ever greater than 0. I'm guessing that's what this, if the drag and the drop are greater than 0, then sort of our rate of change is not negative, and therefore the velocity will never drop, and therefore yes. Okay, so that makes sense. So this assertion here is all about making sure that we don't try to print out none values. So this isn't actually preventing the infinite loop from happening. This is basically a reporting issue. So we don't have tests for any of our reporting code yet. Probably get to that in the third episode. But right now, we can at least be sure that this will not cause an infinite loop. So we're going to say test, let's see, test ball that never stops returns none values. Okay. And okay, fine. We'll do that. And then we're going to say this is none and assert seconds is none. Okay, very good. All right, so we could keep going here and try to test some other things about this. It's probably worthwhile testing some of the sort of usual conditions that you think about when you're doing sort of boundary tests, testing, 0, negative values, positive values, testing things like that. But the main question to ask yourself when you're working with existing code and you're trying to add tests for that code, and this is also actually also applies when you're writing tests for new code, which is if I write a test, what code is it actually going to exercise? What code is it going to assert exists? And so one great way to do this is to go in and make a change to the code that you expect to cause a failure, right? And see if it does. So if I take this if I change gravity, right? So if gravity is now all of a sudden 30 inches per second, or 30 times 12 instead of whatever, I do get a different value there. So that's a good sign. So I broke the code, and the tests failed. That's exactly what I want to see. I want to be very careful that I don't over-specify, that my tests are exhaustive, that we're testing everything we care about, but nothing that we don't. So if this behavior here is correct and we can't really think of anything else that it needs to handle, it's possible that this test by itself is sufficient to do that. Well, these two tests by themselves is sufficient to do that. And one way that you can sort of think about this is look at the conditionals inside of the code. What are the parts of the code where it's going to branch, or its behavior is going to change based on the data. So we have this here. That's something that we're covering. If I take this out, I should be able to see that my test or my code in fact does go into an infinite loop. So we were correct in that, right? So if I change that back, PyTest watch restarts, and it's now running my tests. But if I take this code out, I can see the code goes into an infinite loop. If I were to change this while statement to an if, what would happen? Nope, still fails. Okay, that's good. So I'm having kind of a hard time finding some code in here that would be, kind of exercised by a test. I guess one thing we could do is we could test this. That is probably not tested in one of our existing things. So if I say def test can specify the initial velocity, and I say this, and I'm going to go and say this is going to be 140 104 inches per second instead of the default of 72. And I'm going to go and I'm going to actually verify again, because we're taking it for granted right now that our program works. If we didn't have that guarantee, that we would have to validate this in some other way. But if we say Python 3, golf, Stimpmeter, 210, and then 144, we do in fact get 144 inches per second. And we see that the distance seconds is in fact these values here. So we're just going to grab that for our distance. Seems plausible, just sort of a quick sanity check here. If you're hitting the ball twice as hard, it goes almost 4 times farther. I think that's about right, given the physics of this particular of putting. And then that's going to take 5.2 seconds, so it takes twice as much time. So that seems at least plausible to me. So I run that, and that seems to work. And now if I were to come over here and delete this code, I would expect that test to fail. And it does. It says that it's being given the wrong number of positional arguments. Cool. So that's good. That's good. So yeah, so I can't really find any other things in this function that are really calling out to me for a test. That's not to say that you couldn't test more, and that there aren't things in here that are maybe worth testing. But sort of my initial pass here is sort of looking, okay, well, the only conditionals are here and here. We've got our signature that we're checking. Maybe there's some specific things about this problem that we're modeling that call out for particular values to be checked. But we don't want to overspecify this. We want our tests to be exhaustive, but we don't want them to be overspecified. If we were to change this calculation, if we were to figure out, for example, that our coefficients of friction were wrong, and we were to come update them, how difficult that's going to be is going to be a function of how many tests that we've created. If we've created the right number of tests, then it will be just as hard as it needs to be and no harder. If we've overspecified the testing of this function, then we're going to have we're either going to have to delete those tests, in which case, why did we have them in the first place? Or we're going to have to go update all the values for all those different tests. And if those tests aren't driving out any new or interesting code, what are they really doing? So I actually kind of feel pretty good with this. With just 3 tests, we've kind of covered most of the things that I would be worried about in this function. However, there are still plenty of things in this code that are not being tested. All of this, for example. And how we deal with that is what we're going to look at in the next episode. So stay tuned, and I'll see you all next time.